Okay, let's take a look at question 7.21, and I want to take a look at C. Here it says, identify the major and minor products for the E2 reaction that occurs when you treat this substrate with a strong base. So it could be any strong base. We could choose, hydroxide or ethoxide. It doesn't matter. We're just choosing a strong base. And we're doing an E2 elimination reaction. So if we look at the alpha carbon, this is the one that the bromine is attached to. There's my alpha carbon. You can see I have a beta carbon here and a beta carbon here. The beta carbon on the right has no protons attached to it whatsoever, whereas the beta carbon on the left does have one proton attached to it. Therefore, this is going to be a stereospecific reaction, and it's going to produce only one stereoisomer. And what we need to do is we need to look down this carbon-carbon axis and draw a Newman projection of what we see when we look down this carbon-carbon bond. And we need to adjust that Newman projection to a conformation where the proton, okay, so let me just circle that in green. So the proton of interest in the leaving group, we need to adjust those so that they are anti-periplanar to each other. So I think the best thing to do is to start by drawing a Newman projection of what we would see when we look down that carbon-carbon bond. So you can see the phenyl group is going to be pointing straight up. Our methyl group is off to the left. Therefore, the proton of interest for our elimination reaction is going to be going to the right. On the alpha carbon, the carbon the bromine is attached to, you can see that I have a tert-butyl group coming straight down like this. My bromine is going to be off to the left like this, and then I have another proton over here. So you can see that right away, the bromine and the hydrogen that are involved in the E2 mechanism are anti-periplanar to each other already in this conformation. Therefore, we don't have to adjust the Newman conformation in any way at all. So if I remove those two atoms and I form a double bond here, when I form that double bond, what I'm going to see is that the phenyl and the hydrogen should be on the same side of the double bond, and the methyl group and the tert-butyl group should be on the same side of the double bond. So what I'm going to get as a product, I'm just going to draw it, I'll draw it like this first for simplicity's sake. So I'll put the phenyl group over here. Then I have my double bond, and you can see again, this proton should be on the same side of the double bond as the phenyl group. And then the tert-butyl group, here's the tert-butyl group down here at the bottom, that should be on the same side as the methyl group. Oops, let me just clean up that bond a little bit. There we go, there's our tert-butyl group. So if I just rotate that by 90 degrees this way, so if I draw it maybe a little bit prettier, what you can see, again, here's the proton. I have my tert-butyl group over here, and my methyl group down here. So what you can see is that in this case, in this elimination reaction, what I've formed is the E stereoisomer. So this is the only stereoisomer that's going to be observed in this reaction. So this is a stereospecific reaction because my beta carbon, which contains the proton, is a chiral center.